Okay, this chapter is about modular arithmetic, and the chapter begins with several examples. There are many cases in real life where you count around a circle. Think about a clock. A clock has 12 hours. You count around the circle. You go 1 up to 12, and then you go back to 1 again. Think about an odometer. The odometer starts at 0, and it goes up to a certain number. The old odometers only go up to 99,999, and then it goes back to 0 again. Think about the days of the week. You go from, if you number the days, Monday as 1, Sunday as 7, you go 1, 2, 3, 4, 5, 6, 7, and then start over again. So you're counting around in a circle. So there really are many examples of this. And you can do mathematical problems involving these things. Like if we take this example, if you have a race car that's driving around a 5-mile track and he starts at 3-mile marker and makes 17 consecutive runs of 24 miles, which mile marker does it end up as? Now it's a 5-mile track, so there are only 5-mile markers. He has to end up at one of the 5 miles. You could do this conceptually just by thinking about how many times he's going to go around the track and how much time how much left over is going to determine what mile marker he ends up at. But you really are counting around in a circle. Okay, this idea of counting around in a circle is what we know as modular arithmetic. Now, in that racetrack example, you count, if you have a 5-mile track, really you should start at the 0 mile marker. If you think about it, there's going to be a 0 mile marker, 1 mile, 2 mile, 3 mile, 4 mile, so you can only count up to 4. In this case of a 5-mile track, that means that there's 5 possible answers. This is called the modulus. Okay, so I repeat again that if you have 5 possibilities in a 5-mile track, that means the modulus is 5. Note that the mile markers only go up to 4, but there's 0, 1, 2, 3, 4 makes 5 possibilities, so the modulus is 5. Okay, so let's continue with this example. Here's a picture of the track, and we can talk about the net displacement, which is basically where he is on the track, and it's going to be either 0, 1, 2, 3, 4. Now that may not be the total displacement. The total, if he goes around the track 100 times and ends up back at 0, his total displacement would be 500, but still his net displacement is going to be 0. So here, if we talk about total displacements, if we start at 0, we could go 100 miles forward, or we could go 100 miles backward, or we could do some combination of the forward and backwards. But if we consider where we end up on the track, you can see that these total displacements would correspond to these mile markers on the track. If I go a displacement of 5 miles, I'll end up back at the 0 mile marker. So corresponding to this number line, we have a new modular number 9 line where you have the numbers 0, 1, 2, 3, 4 repeated again and again. Now, some examples here. Suppose you travel 8 miles in the forward direction, or 23 miles in the forward direction, or 17 miles in the backward direction. If you work it out, in any case, you're going to end up at the, well, let's see where you will end up. If you go 8 miles in the forward direction, you go, this is going to be 5, 6, 7, 8. You'll end up at the 3-mile marker. If you go 23 miles in the forward direction, you'll go around 1, 2, 3, 4 full times, and then go 1, 2, 3, end up at the same place. So you're ending up at the same net displacement. Okay. We say two integers are equivalent basically if you end up at the same net displacement. So the formal definition, two integers a and b are equivalent mod m if both a and b have the same remainder when divided by m. Okay, let's see how that works in our example. If you have 8 or 23, we said the modulus is 5. If you divide 8 by 5, you have remainder 3. If you divide 23 by 5, you have remainder 3. If you divide minus 17 by 5, well, minus 17 is minus 20 plus 3. Minus 20 is divisible by 5. So minus 17 also has remainder 3. Remember, the remainder has to be a number between 0 and the modulus. We're always taking positive remainders. Okay, so we say two integers a and b are equivalent mod m if both a and b have the same remainder when divided by m. So these are examples, all of which have the same remainder when divided by 5. So we say that a, 8, and 23 are equivalent mod 5, 23 and minus 17 are equivalent mod 5. In fact, all these numbers are equivalent mod 5. Now, the fact that there is a unique remainder between 0 and the modulus minus 1 is actually a fact that needs to be proved. Okay? We're not going to prove that here. I'm sure you've seen it before. You've used it in high school. Some of these facts that seem to be simple actually take some proving, but we're not going to do that here right now. We'll just take that as a fact that's known. But you should be aware that this is a fact that does formally need to be proved. Notice also the use of 3 lines here to denote equivalent mod m. All right, of course, we said that 8 was equivalent to 23 mod 5. Now, of course, 8 is not equal to 23. We're saying in some sense they're equivalent. It's kind of like equals, but not the same. So that's why we use 3 lines instead of 2. So it's supposed to connote the idea of equality, but not exact equality. Here we also note that equivalence depends very much on the mod of the modulus by which the equivalence is calculated. Here's some example. 3 is equivalent to 8 mod 5. They both have the same remainder when divided by 5. This has remainder 3, and this has remainder 3. But 3 equivalent to 8 mod 3 is not true because 3 has remainder 0 when divided by 3. 8 has remainder what when divided by 3? I guess it's 2. So they're not equivalent mod 3. So be careful when you're doing modular equivalence. You have to be careful about the modulus itself. Okay. Now there's another way to determine modular equivalence. You can go through this argument here and show that we defined originally that a is equivalent to b mod m if they both have the same remainder when divided by m. Another way to show the same thing, and you can read the proof here, is that a and b will have the same remainder when divided by m if and only if a minus b is divisible by m. Okay. And we go through the proof here. Please read the proof on your own. And we want to show that a equivalent to b mod m is the same thing as saying that a minus b is divisible by m. So you have to show this actually both ways. You have to show that a is equivalent to b mod m implies a minus b is divisible by m. That means that this statement, if this statement is true, then this statement is always true. You want to show the reverse as well. That will show that these two statements, a equivalent to b mod m and a minus b is divisible by m, are actually equivalent. So this is what's called an if and only if statement. Here we show the if part. The only if part is exercise 17, where you fill in the blanks. And the result of proving the if part and the only if part gives this equivalence between, shows that these two definitions are the same. A equivalent to b mod m, if and only if a minus b equals k times m. That's the same thing as saying that a minus b is divisible by m. Here's a shorthand notation. A minus b is divisible by m can be written this way. M divides a minus b. And let's go on to the next fact. All right, so this proposition, given any integers a, b, and c, and a positive integer n such that a is equivalent to b mod n and b is equivalent to c mod n, then it's also true that a is equivalent to c mod n. Now, if you replace these equivalences with equals, you could see this is a property that's true of equality. If a equals b and b equals c, then a equals c. Here we're showing something more general. The same thing holds for modular equivalence. This is called the transitive property. So you can use the definition of modular equivalence to show this. That's one of your problems. Okay, some more questions here. For instance, this question here, suppose January 25th is a Thursday. Use definition 13 to determine whether January 3rd is a Thursday. Now remember, here we're talking about days of the week, so you have to think about what's the modulus in this case. Well, you've got Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, 7 possibilities. Your modulus is 7, so that's the modulus you're going to use on these two numbers, 25 and 3. Okay, so you should be able to show this using these concepts of modular equivalence. All right, so now let's consider some arithmetic problems involving these modular numbers. Here's an example here. Dusty drives around a 5-mile track, 112 miles in the positive direction, 49 miles in the negative direction, 322 miles in the positive direction. To find Dusty's net displacement, well, you could add up the numbers and take the remainder mod 5. That's one way to do it, but there's actually a simpler way. You could take the remainder of 112, which is 2. You could take the remainder of negative 49, because he's traveling in a negative direction. We take negative 49. Remainder of negative 49 is 1, because minus 49 is minus 50, plus 1. You could take the remainder of 322, so that's going to be 2. Okay. Now, instead of adding up these big numbers and taking the remainder, we can actually simply add up the remainders and take the remainder of that, and that gives us the same answer. Okay. We actually replaced the big numbers by their remainder. So this is modular arithmetic, dealing with remainders instead of the numbers that they're equivalent to. The nice thing about this is that if you have a modulus n, say, then the remainder is always less than n. So you're always doing arithmetic with numbers less than n. You limit the size of your numbers, you have simpler arithmetic. Okay. Turns out you can also do this with multiplication. Okay. Suppose you 113 miles an hour for 17 hours. Okay, that's going to give you a certain number of miles, and you can figure out what that is mod 5. It turns out to be 1. Now, it turns out that instead of multiplying these big numbers together, I could take the modular, I could take the remainder of 113, which is 3. I could take the remainder of 17, which is 2. Multiply those two together, I get the very same answer. Much, much simpler, much more direct, but the same answer. Now, can you prove that this is always going to work? Well, you do need a mathematical proof. We're not going to prove it in this section. But we're seeing that arithmetic with remainders is meaningful and useful, and also much simpler than arithmetic with general integers. So we formalize this because we're talking about integers with remainders. Now the remainders, when you're dealing with mod n, the remainders are between 0 and n minus 1. So we're going to call this set of n numbers from 0 to n minus 1, the set of n integers, we're going to call that the integers mod n. So it's a special set of integers, and we use this symbol Zn to denote the integers mod n. So when you see the subscript, you know that you're not dealing with an infinite set of integers. You're only dealing with a finite set of integers between 0 and n minus 1. Okay. Now the nice thing about modular integers mod n, is that in this case, modular equivalence is the same thing as equality. If I take any two numbers in this set and I say that they're modular equivalent, they're equivalent mod n, it turns out that they must be the very same number. And that's kind of intuitive because we've saw before that if two numbers are equivalent mod n, then they differ by a multiple of n, and there's not n numbers here, so two different numbers in here can't differ by a multiple of n. Now you formalize that proof here, you fill in the blanks. It's a good exercise for you, and that's it for this section.